Okay, now let's make a little summary here. We have K, which is what we get. Okay, well, let me start up here. We impose a delta H in our Darcy experiment. Can you see that? Sorry. Okay, there. We impose a delta H. We impose really a L, length of the specimen, and an area of the specimen, because we know the diameter of the specimen, right? So we impose these three things, we decide them, okay? We measure the flow rate, Q. And then with these parameters, we plot and we get K. Now, generally what we do in the lab, generally, we do not conduct various experiments to determine this line and plot, etc. What we do is we impose a very low delta H, and then we do just one test. Okay? So if you think about it, delta H over L times A, Q. We know that if there's 0 delta H, there's 0 Q. And then we run one test, okay, with a low delta H, and we measure Q, and let's say we get that. So if we have 2 points, we can determine K because it's a slope. Now you may say, hold on one second, how do I know that the imposed parameter, this parameter here, is not beyond this threshold? That is, how do I know that the flow is not is laminar and not turbulent? Well, that's a very valid question. Typically, we already kind of have an idea of what are the imposed delta H that we have an idea of what delta H to impose for a given soil, so that we are not in the turbulent regime. So in the field, that is in industry, etc., you typically just run one test with a low delta H, really with a low delta H over L times A, low group parameter here, low value of this whole thing, and determine the Q, and then the K is just the slope. So if you look at this, you write out the equation for this line, okay, you get what? Y is equal to M X plus B, but B is the intercept, which is 0. So this right here is the equation to calculate permeability. Sorry, hydraulic conductivity. At this point, I'd like to make a distinction or make a comment, because I keep on saying permeability even though I should say hydraulic conductivity. And I suffer from this ailment of mixing the two, like all geotechnical engineers suffer, okay? So, the true name of K is hydraulic conductivity. But we can calculate another parameter that is related to K, that is called the permeability, and the geologists do that, okay? They use permeability, we use hydraulic conductivity. But we generally use, that is we, geotechnical engineers, we use hydraulic conductivity and permeability, we use both words to describe the hydraulic conductivity, both terms. So the correct one is hydraulic conductivity, okay? But generally, we also use the word permeability for hydraulic conductivity, even though it's not really the same thing. Now you may say, okay, why are you saying all this? We should use the correct name, right? And that is true. We should use hydraulic conductivity for this K. But, like I said, if you go out to the field and start talking about this, the geotechnical engineers will start saying permeability to this, okay? So you have to adopt, basically. Adapt. Adapt. You have to adapt to the fact that geotechnical engineers will use this word for the hydraulic conductivity, as well as hydraulic conductivity for this K. Okay? So if you hear me saying permeability, what I mean is hydraulic conductivity. Okay, so this here is the equation to calculate K. Look, we know delta H because we impose it. We know A and L because we impose it, or them. We measure Q, so we can get K. Okay? And, sorry, this is what you see in this slide, which is the slide just after this one, right? That equation is called Darcy's law, the one we just wrote down. Okay? Q is equal to K times delta H over L times A. Remember the gradient? I, we said the gradient was delta H over delta L. Well, for the case of a finite problem, which is the Darcy's experiment problem, which we run daily in the lab, this is delta H over L. Okay? So now we have a new definition of hydraulic gradient that you have to know, which is, it's not a new definition, it's a modified definition, which is the change in head, or the head loss, that's called the head loss, as well as the change in head, or the total head difference. You can call it whatever you want, as long as you call it one of those three. Head difference, head loss, or total difference, difference in total head, okay? Divided by the length over which the head is lost. So remember that head is energy. So as fluid flows through a soil, it loses energy because it's grinding against the grains, okay? So that's why we call this head loss. So the head loss, or difference in total head, divided by the length over which the head is lost. What is the length over which the head is lost? It is the length of the specimen. Because the energy that is lost through fluid flow is lost as the fluid travels through the soil. Now you may say, from your fluid mechanics course, you may say, look, you are disregarding the tubes, because when fluid flows through a tube, it also loses energy. That is true. But here we can disregard the energy lost through the tubes, because those are very smooth tubes, and the energy that is lost by the water, in this case flowing through the tubes, is very small compared to the energy that is lost as the fluid flows from point 1 to point 2. That is across the soil specimen, or through the soil specimen. Okay, so here's Darcy's law. We know that it applies to laminar flow, and we know that we should use it, or it only applies when the soil specimen is not changing because of the flow. So let's think a little bit about this. Let's go back to our previous slide and realize that if we have a rather, let's say that we have a rather intense flow, so a high flow rate, you could think, or without, intuitively, it would be correct or reasonable to think that the flow imposes drag forces that can actually move the grains around inside this cylinder, okay? If that happens, if particles are moving around in there, then the soil as a unit, or as a fabric of particles, is being changed. That is, the fabric is being changed by the water flowing through the specimen. Okay? That is something that can happen, but that renders the definition or the determination of K for that test null. Why? Because the determination of K is, or the K that you measure, is the K for a soil, for a given soil, not for a soil that has changed because the water has changed the fabric of it. Okay? So the assumption for the validity of this law is that the water doesn't change the soil fabric, or the packing for coarse grain, fabric for soil, and fabric for fine grain soil. We can use the word fabric for both. Okay? It doesn't have to be packing. The fabric, that is the way the particles are assembled, If it changes because of the flow or changes because of time, right? Maybe some particles are decaying in there while you do the test. If that's the case, then the K that you measure is not really a true K because the soil is changing. Okay? So these are the two main assumptions that we need to fulfill for applying this equation. Hydraulic conductivity, hydraulic gradient, cross-sectional area of flow, which is pi r squared for the case of a cylinder, okay, and Q, which is what we measure. That is summarized in this slide. How do we determine the hydraulic conductivity of a soil? Well, the soil is taken to the lab, the specific soil that we want to test. Okay, we prepare the specimen, we impose a gradient. What's a gradient? Delta H over L. We know A, right? So we impose that too. We measure the flow rate and then determine K with Darcy's law. Like this. Q is equal to KIA. So K is equal to Q over IA. It's the same. You need to memorize this equation. Very simple. This is the car. Remember the car? Kia? Well, Q is equal to the car, Kia. You will never forget it. Okay? That's a kind of an easy way to memorize it. So this is the way that we determine K. Now, if you go back to the previous slide, you'll realize that K is in units of velocity. Let's actually do it right here. Look, here. This is meters cubed per second, or centimeters cubed per second, whatever you want. This is meters squared times I. I has no units, because I is equal to meters over meters. No unit. So that 3 cancels with this 2 and this 1. So you end up with meters per second. K in meters per second. So the units of K are units of velocity. Generally, we report values of K in centimeters per second. Okay? Now, it is important to realize that even though K has units of velocity, it is really not a velocity. It is not the velocity of the fluid. Okay? And I'm going to ask you, I could ask you that on the test. Is K the velocity of the fluid as it flows through the soil? The answer is no. Okay? K is a proportionality parameter. K is the proportion between Q and this group. Proportion. Okay? It is not a velocity. So have that in mind. Next slide. We talked about this before, but let's kind of talk about it in a formal way. So before we go on to this, which we talked about kind of, let's kind of have some kind of definition for or description of what K is, the hydraulic conductivity. It is a measure of the resistance to flow of a soil fluid system. Now, why do we say soil fluid? Why not just a soil? Well, because like we said earlier, K depends on the soil type or the soil properties, dense sand, loose sand, clayey sand versus just sand, etc. Right? But it also depends on the fluid that flows through the soil. If you have, if you think of, for lack of a better for lack of a better example, because I don't know if you are aware of or you have seen petroleum, which is a very common material that flows through soil. But I don't know if you have actually seen petroleum, but I know that you have probably seen honey. So if you have honey flowing through soil, it's going to flow much slower, okay, than if you have water. So when you run the Darcy's experiment with honey versus water, you're going to get a low K for the case of honey and a high K for the case of water for a given soil. Okay? So K is dependent on both the soil and the fluid. What are the soil properties that affect K? The sizes of the pores. Why? Because the fluid has to flow through the pores. It doesn't flow through the particles. It flows through the voids, through the pores. the fabric, how the particles are assembled, that dictates how the voids are interconnected to each other. So these two are related. Remember, pore and void are the same word, are the same thing. Okay? And it's also important to realize that the fluid will drag, it would grind against the surfaces of the particles. Okay? So the more surface there is, the more drag there will be, and the lower the K will be. Okay. Now, in the case of, for the contribution of the fluid to K comes through the viscosity. So the viscosity is the parameter that controls how the fluid affects the K. So honey has a very high viscosity. Water has a low viscosity. Air has a very, very low viscosity. So depending on what fluid you have flowing through the soil, that will alter or change your value of K, hydraulic conductivity. All right. Now, we have talked about how to determine K in the lab, because that's generally what we do. We use Darcy's experiment, and we replicate it in the lab for our soil. We use water, and we determine K with Darcy's law. But there are ways to actually do this in the field. Okay, there are ways to determine the permeability of the soil in the field without having to take it to the lab. This is much less common than taking it to the lab. So all I have here essentially is a list of the names of the two tests, the two most common tests for measuring K in the field: the slug test and the pumping test. Okay, I'll let you read those the descriptions of these tests in the book. Okay, but for the sake of this course, it's most important that you are well versed and that you understand the determination of K in the lab. Okay, this is done with the well systems, etc. Okay. Next, typical values, very important. In geotech, we always want to have in mind a toolbox of typical values for different parameters. Clearly, K depends on the soil. Now, we said before that it depends on the fluid. So this is K for water. Okay, these are typical values for the flow of water through soil, which is by far the most common case in geotech engineering. Gravel, 10 to the 1 to 10 to the 2. Sands, 10 to the minus 3 to 10 to the 0. That means 1 centimeter per second. Silts, 10 to the minus 8, 10 to the minus 3. Clays, 10 to the minus 10 to 10 to the minus 6. So look, the lowest, it's about 10 to the minus 10. It could actually be 10 to the minus 12 or something like that for clay. And for gravel, 10 to the 2. Sometimes even 10 to the 3 if the gravel has large grains. Okay? So this is 12 orders of magnitude difference from here to here. That's enormous. So this is the parameter that varies the most for soil. Okay? This parameter is very, it has a very wide range. Now, clearly the typical values are important, but something to be very careful of here and to make sure that you understand is that when we report values of K, because the K varies so much across soil and its range is so large, 10, 12 orders of magnitude, 14 orders of magnitude, we report the value of K with maybe 2 digits and a order. Okay, so for example, you could say you would find in the field, you talk in the field meaning in industry, you could ask a geotech engineer, okay, you have some gravel layer, okay, what is the permeability, or sorry, well, you can say permeability, they will understand. So you can say, what is the permeability or hydraulic conductivity of the gravel? Okay, and the engineer will tell you, okay, it's 5.2 times 10 to the 2. Okay? If the engineer tells you it's 5.27935, times 10 to the 2, then you have to look at that engineer with a kind of a funny face, because it is very difficult to know for sure if the value that is next to this 2 is correct or not. Sometimes even you would say 5 times 10 to the 2. Some people would even say, forget about this 5, 10 to the 2. That's the hydraulic conductivity of the soil. So please don't get caught in reporting permeability values with more than one significant digit after the point. Okay, 5.3 times 10 to the minus 8, fine. 5 times 10 to the minus 8, that's fine. 5.37 times 10 to the minus 8, that's no longer fine. You gotta remove that 7, make this a 4. If this is a 7.37, that is a 4. 5.4, etc. Okay, so you get the point. It's just a way of reflecting that you know the range of sizes that, the range of K values that you can have, and that it's very difficult to actually measure to such high accuracy the permeability or hydraulic conductivity. Remember that I said that we can interchange the names, even though the correct name for K is hydraulic